Good morning, children. I appreciate that most of you had sent your homework of 31st. Good that you've taken some efforts. Please keep continuing. Okay. Today there is some portion left out in this chapter, refraction through lens. I thought of finishing that. First of all, just note down the change in the syllabus. In page 103, power of a lens, concave and convex. Um, you can cut off the next two lines, that line and this line. And in power of lens, only definition and basic understanding. Only definition and basic understanding. No need for numericals. Earlier they used to have simple and direct numerical problems. Now that is not there. You just need to know the definition and basic understanding. Okay. Now, so where is that? That's the last part of the um, C part. Power of a lens. B part, sorry. Power of a lens. Now, what do you mean by power of a lens? You all, those of you who are wearing spectacles, know something called the power. Okay, that only tells about how much your glass will bend a ray and things like that. Okay, so that is called power of a lens. That's called power of a lens. So what is power? The deviation of the incident light rays produced by the lens on refraction is a measure of its power. Generally, it tells us how much the ray deviates after hitting the lens. Okay, now here is the important thing. A thick lens, a lens having surfaces of more curvature, is of short focal length and it deviates the rays more. A thick lens. So imagine you have a thick lens. Okay, so that means it is formed by two spheres. Okay, so the more it is thicker, the more it will be closer to the center of, these are your center of curvature, C1 and C2. Okay, and this is your optical center. Now where will be F? Exactly in between these two. Now because its curvature is more, already C2 will appear to be closer. So F will also be closer to the lens. Hope you understanding this. Because this curvature is more, when I finish the two spheres, the center will become very close to this surface. Okay, so as we know that F comes in between optical center and center of curvature, it will be very close to the mirror. The sense, in case of the focal length being very closer, so what will happen to the rays? They will deviate a lot because they have to have a sharp bending, right? Parallel rays will pass through F. They have to bend in a sharp way. Sorry, that is what is given here. A thick lens will have short focal length and it deviates the rays more. Whereas, okay, so two things: thick lens, short focal length, and deviates the ray more. While a thin lens is of large focal length and it deviates the ray less. Hence, power of a lens is expressed in terms of, okay, in terms of reciprocal of focal length. So the formula for power of lens is 1 upon focal length. Okay. Now here another thing, unit of power of a lens is called diopter. Okay, and its symbol is capital D. Diopter, capital D. Okay, and the formula, okay, so power of lens will be in diopter, 1 upon focal length. It's important to write in meter. Okay, so when you generally substitute it, anyway, you're not going to have the numericals, but it is important to mention in meter, in diopter here. Okay, while giving a prescription to a patient, an optician does not quote the focal length of lens, but he or she quotes the power of the lens. Okay, so they will actually give the power of lens. Based on that, the opticians will find out, they'll calculate how much should be the focal length. Accordingly, they'll give you the spectacles. Okay, So power can be either positive or negative. So power of a convex lens is positive and that of a concave lens is negative. You'd have heard some people saying my power is plus 2 or minus 2. So that means if they are a positive, then they are wearing a convex lens. If it is negative, then they are wearing a concave lens. Okay, so this is all about power of lens. Actually, there are 4 numericals I think in the exercise. You can just cut it. 11, 12, 13, 14. Okay. Then the last part, okay, in the syllabus, there is one part there, application of lenses. Okay, application of lenses is still there. This part is cut, but there is application of lenses is still there. That's not cut. Okay, so that's in the C part actually, D part, and most of it is cut, like magnifying glass or simple microscope. So you can cut off all this. Only this portion is there. Application of lens. So only this part is here. Rest all to be cut off. Okay, this also experimental determination of focal length. All that you can cut off. And similarly you can cut off this also. In the last page you have, actually this we will be doing in practicals. Okay, when you come to school we'll be doing in practicals. And okay, these all will be in practical, and then this is not there again. For theory you need not study anything of this. Okay, so happy, most of it is cut. You need to study only a small portion. Okay, now let's study what are given in the application of lenses. So objective lens, telescope, camera, slide projector, they all have convex lens. Our eye lens is a convex lens. You would have studied in biology. The eye lens forms inverted image of the object on our retina. Now comes the very important point. That is, there are two eyesight problems. One is called long-sightedness, other one is called short-sightedness. Now long-sightedness, other name is hypermetropia, and short-sightedness, myopia. Okay, now so what is long-sightedness? People can see long distance things clearly, but they cannot see short distance things. And that's opposite in short-sightedness. They can see nearby objects clearly, but far away objects they cannot see clearly. Okay, now, so depending on the eye problem, they will give you the spectacles. Okay, so if you're suffering from long-sightedness, you have to wear a spectacle of convex lens. Okay, spectacle of convex lens. If you're having long-sightedness, spectacle of convex lens. And if you have short-sightedness, you have to wear a spectacle of concave lens. So these are the two things you have to remember. To overcome long-sightedness, you to wear convex lens. To overcome short-sightedness, wear concave lens. Now, sometimes some people have both long-sightedness and short-sightedness. Okay, then they don't. Sometimes you could have seen there are people wearing two glasses, or in one spectacle itself they have something called bifocal lens. Okay, the lower part will be convex and the upper part will be concave. Okay, so the lower part is convex, used to see nearby objects, while the upper part concave, used to see distant objects. Okay, a magnifying glass is basically a convex lens. That's another use. Collimator of a spectroscope. Okay, this you'll be studying in 11th and 12th. So you just spectrometer or spectroscope. And then concave is used as eye lens in Galilean telescope. A single convex lens usually forms a colored or blurred image due to chromatic aberration. Combination of concave and convex lens is used to overcome such a defect. Now the main thing is these 6 are the main applications. Okay, so with that this chapter is over, but I had left something in part A, so I want you to turn to page 107. Page 107. Now, as I told you, from this part, generally they don't ask any question like definitions of focal length or focal point. They don't ask such things. But there is one, some information is given towards the end as note. From this, many questions come. So I wanted to discuss that. Now, there are generally a lens can have two focal points. Okay, first focal point and second focal point. Okay, for convex lens, first focal point is on the left hand side. Now why do I say it can have two focal points? Because if parallel rays come from here, they can meet this side and this becomes the focus. The same lens I can also use for rays coming from here, and the rays will all meet here. So this can be the focus. So now for convex lens, this is called first focus. The one on the left hand side is called first focus, and one on the right side is called the second focus. This is the second focus, and in our diagrams we use only second focus. This is what we use. We don't use the first focus, we use only the second focus. Same way for concave also, first focus will be to the right and second focus will be to the left. Second focus will be to the left, and we always use second focal point for concave. Okay, so now the important things that we have to, so all the note, every point is important. If the medium on both sides of a lens is same, its first and second focal length are equal. If medium on both the sides, if this side is also air, this side is also air, then these two focal lengths will be same. If this is 2 centimeter first focal length, then second focal length will also be 2 centimeter. Okay, if the medium is there. Now if suppose one side is air, another side is water, then it might change. Okay, then okay, usually when we say focus, we mean second focal point. I told you, according to the ray diagrams, for the ray diagrams that we drew, we took for convex this right side one as the focus and for concave the left side. So we are considering the second focal point. Okay, third one, this is a new term, real focus and virtual focus. Virtual focus. Now convex lens has real focus. What does it mean? The rays parallel, after refracting they meet at F. That's called real focus. Virtual focus is of concave because parallel rays incident on convex after refraction do not actually pass through, but they appear to diverge from this point. You know that. So this is these are two terms, real focus and virtual focus. Okay, then these diagrams, you know, if the rays are not parallel, this is object at a far away distance, so you will not get a exactly at the focus, you will get a image here on the focal plane. This is called focal plane. Okay, then the last two, the same thing they have given for concave also. Then fifth point, factors affecting focal length. Factors affecting focal length. There are two factors affecting focal length. One is refractive index of the material of lens relative to its surrounding medium. Refractive index, that only determines how much the ray will bend. If a lens is placed in water instead of air, that is, if mu decreases, its focal length increases. Okay, and vice versa also. Second point, radii of curvature of the two surfaces. A thick lens has less focal length, thin lens has more focal length of same material. Then sixth point is also an important thing. What will happen if a part of a lens is covered? Okay, what will happen if part of a lens is covered? Okay, so two things you have to write. One is focal length will remain unchanged. Focal length will remain unchanged. Only the amount of light entering the lens decreases, due to which intensity of image decreases. Now what does it mean? Suppose this lens, I am covering half of it, okay, with a black paper or cloth or something. Okay, so I've covered this much, only this part is functional now. Okay, so what will happen, the focus will not change, focus will be the same, but the intensity of image will be less, because the rays that are coming here, they are not going to get refracted because of this thing, but only the rays coming from the upper part, they will all meet. So the intensity of image will be less. intensity of image formed by the lens decreases, but the position, size and nature are all remaining do not change. They all remain the same. Okay, children. So that's all um, about this chapter. We have done everything. So there are 4 more numericals left. Please try them as homework today and send it to me. Okay. Question number 5. Okay. 5, 7, 17, 18. 5, 7, 17, 18. So these are the homework for today. 5, 7, 17, 18. In this, I would just like to say a little bit about the 5th one. It's a little different. An illuminated object lies at a distance 1 meter from a screen. Okay, so they are saying an object lies at a distance 1 meter from the screen. Now this is your screen. This is where the image formed. Okay, so this distance 1 meter or 100 centimeter. Then a convex lens is used to form an image of the object on a screen placed at a distance 75 centimeter from the lens. So screen is placed at a distance, so there is a lens in between, and that this distance is 75 centimeter. So what about this distance? 25 centimeter. So U and V are given. Hope you understood. Just the wordings are little different. Same way, 7th one, a lens forms the image of an object placed at a distance of 45 centimeter from it on the screen. A lens forms an image of an object formed at a distance. Lens forms the image of an object placed at a distance 45 centimeter from it. So the object is placed at a distance 45 centimeter from the lens, and it forms an image on a screen that is 90 centimeter from the screen. Yeah, so again U and V are given, so you can solve it. Okay, so please do these 4 numericals: 5, 7, 17 and 18. Thank you, children. Okay, before I finish, hope you're all preparing for Saturday's test. So if you have any doubt, you can WhatsApp me and ask. Okay, so prepare thoroughly for the test. Thank you.